analyze the role and effectiveness of buffer systems in maintaining pH stability within an industrial process. The role of buffer solution is a solution that minimizes changes in pH when small quantities of acid or base are introduced. Buffers are essential in biological systems as they maintain the ideal pH for cellular activities and safeguard delicate molecules from pH variations. The effect of buffer systems help regulate the pH within optimal ranges, which is essential for the activity of microorganisms involved in biological treatment methods like aerobic and anaerobic digestion. Buffer system stable pH levels prevent the inhibition of enzymes and microbial activity, enabling effective breakdown of organic matter and nutrient removal. Discussing potential challenges and solutions. Our focus today is on emerging pollutants, operational costs, variable influent composition, and environmental regulations. Now, let's talk about the challenges. Emerging pollutants are a growing concern, as they can have adverse effects on human health and the environment. Operational costs can be a significant factor, especially when it comes to energy consumption and maintenance. Variable influent composition can also pose a challenge, as it can lead to fluctuations in the quality of the effluent. Finally, environmental regulations are constantly evolving, and it's crucial to stay up to date to ensure compliance. So, how can we tackle these challenges? The solution lies in dynamic buffer systems, innovative materials, energy integration, and advanced treatment methods. By implementing these solutions, we can ensure the sustainability and efficiency of our environmental systems. Now, I will be discussing how acid-base equilibrium principles are applied in wastewater treatment processes, highlighting the vital roles they play in ensuring water quality and environmental safety. First, let's talk about pH control. This aspect is critical as it affects the growth and activity of microorganisms, which are essential for effective biological treatment systems. Next, chemical reactions. Acid-base principles influence the rate of these reactions, particularly in advanced oxidation processes. These are crucial for breaking down harmful substances in wastewater. Another key concept is alkalinity, which measures the buffering capacity of water. It helps maintain stable pH levels, ensuring that wastewater treatment systems operate efficiently. Finally, neutralization processes, such as using sodium hydroxide, adjust the pH of wastewater with high or low levels to make it safer for discharge or further treatment. Next, I will be walking you through the neutralization process for industrial effluents containing both strong and weak acids. This process is critical for ensuring environmental safety and regulatory compliance. Let's dive into the key steps involved. This is the starting point of the process. First, we determine the effluent's pH, concentration, and type of acids present. Then, we measure the effluent flow rate to plan the treatment process. Finally, we identify any impurities that could impact the neutralization process. Next, the effluent undergoes screening and filtration to prepare it for treatment. Settling is allowed for precipitates to form. Advanced systems like sand filters or membrane systems are used to remove residual solids. The core of the process happens in the neutralization tank. Here, acidic effluent with low pH or basic effluent with high pH is neutralized. Additionally, this step facilitates the removal of heavy metals, which are hazardous to both human health and the environment. After neutralization, the effluent flows into the settling tank. Suspended solid particles are separated from the wastewater. Both organic and inorganic solids are removed before biological treatment. Settled solids, or sludge, are collected at the bottom for proper disposal. Then, polishing filters are used for final cleanup. They remove fine particles, residual suspended solids, and microcontaminants from the treated wastewater. This step includes tertiary treatment to meet regulatory standards for water quality. It also ensures microbial control to reduce bacterial or viral load. Finally, the treated or untreated effluent is discharged. It is released into water bodies or sewage systems, ensuring minimal environmental impact. At excess rainwater or runoff is managed to prevent flooding. Sometimes, water is discharged into aquifers to help replenish groundwater levels. To wrap up, this neutralization process is a comprehensive approach to managing industrial effluents. It ensures that both strong and weak assets are treated effectively, protecting both the environment and human health. For applied acid-base calculations, neutralization is an essential chemical process that balances acids and bases, ensuring it is both cost-effective and environmentally sustainable. Neutralization uses the equivalence point to determine the molarity of unknown solutions. The calculations are relied on the formula NJV equals MEV, where M equals molarity of the first solution, V equals volume in liters of the first solution, M equals molarity of the second solution, V equals volume in liters of the second solution. By applying this formula, you can find the concentration of unknown solutions with precision. This approach is widely used in industrial and environmental applications to optimize neutralization reactions and reduce waste. Besides that, for acid-base equilibrium principles in wastewater treatment, acid-base equilibrium principles are crucial for wastewater treatment to ensure environmental safety and economic efficiency. The first principle is ratio of neutralizer to wastewater, which maintaining the correct ratio minimizes costs and reduces sediment buildup. Tailor the neutralizer amount to the specific conditions of the wastewater. The next principle is cost and basicity of neutralizing agents, which compare the economic and chemical effectiveness of various agents. The common agents include caustic soda and sodium carbonate, which are more effective than traditional lime or limestone. The third principle is using caustic soda or sodium carbonate. These neutralizers are powerful and requiring smaller volumes. Their efficiency reduces overall material and handling costs. The last principle is implementing continuous flow systems. Continuous flow systems are widely used in treatment plants. They ensure a steady and controlled process, making treatment more efficient. Through careful application of acid-base principles, wastewater treatment can achieve cost savings and environmental compliance. This helps industries meet regulatory standards while protecting natural resources.